statistical mechanics. Okay, and what will be the aim of this course is to study mathematical models that exhibit phase transition. Okay, so I will come back to what I mean by phase transition. And the two mathematical models that we will study are going to be percolation. So this we'll have around 1 month concerning the study of percolation. And the second month will be on the Ising model. Okay, so let me first talk a bit about maybe the prerequisite for this course. So, okay, and I put some commas. I will explain why. So, okay, so okay, depending on where you come from, okay, you need basically basic calculus or a bit of analysis, but nothing very advanced. At some point, we will use complex numbers. Okay, and I'm not sure I will go through this, but maybe we will need a tiny bit of complex analysis. Okay, and okay, so you need to know something about probability. So I think an undergraduate course in probability is sufficient. Okay, if you know about the notion of independence, if you know what a sequence of independent random variable is, I guess this should be sufficient. Like, you can interpret probability as sum of finite collection of numbers that sum up to 1. Okay? Probability with a finite state space. And for a couple of arguments, it will be necessary to know about measure theory. So I think the idea is that it's not a problem if you don't understand all the arguments in the course. So if you don't know about measure theory, for instance, you don't need to worry too much. It's just that at some point you will have to accept some of the things I say. I think you can still benefit of the course if you don't know about it. Yes, I think okay, the rest, it's kind of yes, like I think it's part of a standard undergraduate program. So the idea is that the course should be accessible to students from end of graduation. Beginning of master's. Okay, so the idea is to have a lecture that can be of interest to a wide public. So in particular, what this means is that how I'm going to yeah, the level of details will be up to the public, so please ask all the questions you want. This will be helpful to you and also to me to direct the lecture in the right direction. Okay, so what will be the evaluation of the course? So, I will cook up two lists of exercise that you will have to hand to me. Basically, one on percolation, one on the Ising model. I will try to include as many exercises as I can during the lecture. But of course, I would not be able to correct all of them. So, okay, I think for this kind of summer course, well, the validation of the course should not be the biggest objective. So try to practice as much as you can so that you can well, be well in the subject and be able to follow the course and to get the most out of it. Okay, so the idea is that anybody that follows the class should be able to validate, to do some of these exercises. You will be encouraged to collaborate for this. You can resolve it in group. What I will ask is that the writing should be done separately. I don't want to correct several times the same thing. So, maybe what I should give is a list of references. So, okay, so my first reference concerning percolation is in French. So that's, but it's a very good one. So you can still look up to it. It's easy to find on the internet. It's called Percolation et Modèle d'Ising. And it was written by Wendelin Werner, 2009. And I will only, this will be the reference for the percolation part of the course. I will not use the Ising part. There are some lecture notes in English on the webpage of Hugo Duminil-Copin. It's called Introduction. I don't know if there is a date. So just for you to have an idea, here you have about, I think, 80 to 90 pages about percolation. Here you have 30 pages, and it's kind of the same content. So this is much more, it's a bit more difficult to follow because it's much more synthetic, in a sense. But, okay, another good reference is our lecture note from Grimet, which are called Probability on Graph and Networks. So, okay, this is available on his website. Okay, there is also a published version, but I think it's virtually the same. And so here, this goes slightly beyond percolation, but chapter, I think, 3 and 5 are on percolation. also another standard, but older reference is the book from Gumet, which is called Percolation. Okay, so this will be for the first part of the course. And of course, it doesn't mean that I will browse the content of all of these books. I think, yeah, I will do most of what you can find here and on the percolation part in here. On these things, you have a much broader range of, okay, here you have only percolation, but you have a huge range of results. Here you have a larger range of subjects. Well, it can be also of interest to you if you want to explore things beyond percolation. Okay, and for the second part of the course, I will use only one reference, which is called statistical mechanics on lattice systems. Of lattice systems. Okay, and it's by a concrete introduction. Okay, and it's a book by Sasha Friedli and Ivan Velenik. Okay, and well, I don't remember the year, but you can find it on the website of Velenik. So, okay, I mean, basically, these three things, you can find this on the web pages of the author. These things, if you know how to find your way on the internet, you can find them. If not, you can ask me. I'm on the record, yeah, things that I cannot say. Okay, so are there any questions so far? Okay, don't hesitate. Maybe let me know about your background a little bit, so I know some of you, but not all of you. So who is a student of, who is a student of an undergraduate student here? Yes, okay. What year are you in? Third, okay. Okay. So is the prerequisite okay for you? Okay, so this should be fine. Who is a master student here? Okay, and who is a PhD student? Okay, so we have a wide range. Okay, so I hope everybody will be happy with the content of the course. I will try to do my best. And please don't be intimidated. If this goes too fast, let me know. I will try to go slower. If you want some more details about something, I will try to provide it. Okay, and now let me try to go back to this part and say something about phase transition. Okay, so what's a phase transition? Okay, so I did not erase the list of references. Okay, so discontinuity. So I don't know if it's the best definition, but let's start from this. So phase transition is a discontinuity in the properties of the physical system when the parameter varies continuously. So let me give an example to illustrate this definition. So let's look at water at standard atmospheric pressure. Okay, so P equal 1 bar. So if the temperature is larger than 0 Celsius, then the water is liquid. And if the temperature is smaller than 0 Celsius, then the water is solid. And in particular, what you know if you left something for too long in the freezer is that, well, the density of solid water is smaller than that of liquid water. So here, the density is 1 kilogram per liter, and here it's 0.91 kilogram per liter. Okay, so if you maintain the pressure and vary the temperature of the water continuously, you see that there is a property of the system that exhibits some discontinuity, namely the density. Okay, and if you look at water microscopically, it's kind of difficult to understand why this would happen. Okay. At the microscopic level, you know, you have just small molecules. You have some interaction between them, basically. The electronic orbitals of the molecules interact, and you have some. Okay, you have a few interactions between the molecules. The temperature, you know that it corresponds to the kinetic energy of the molecule. So basically, you can imagine that these molecules, they kind of move. And like the temperature is somehow related to the average speed, okay, or to the average kinetic energy of the particles. Okay, and what this is saying is that basically when you decrease the kinetic energy at some point, okay, the molecule will start to arrange it into some crystal structure that will just change the density on the macroscopic level. Okay, and really at the moment there is no mathematical model that fairly accounts for this transition, okay? So even if you simplify a bit the interaction between the molecules, you won't be able to find a model that kind of, well, explain, well, okay, give you kind of give you a rigorous mathematical explanation of why this occurs. Okay? So the idea is for us to look at simpler models that describes kind of other phenomena. So these are the two models we will be focusing on, so percolation and the Ising model. So what is percolation about? I will come back to this a bit later, but for the moment, let me say that. It's about modeling a porous medium. Okay, so a material with some micro holes, and you want to study basically the conductivity of the whole, the system of holes in the material. Okay, and the Ising model. Which models magnetization of a metal. Okay, so these look like very specific problem, but I have to insist that these things have been like models that have been of major interest for the mathematical community in the last 70 years, and even more in the last, say, 30 years. So in particular, so in the last 20 years, 3 Fields medals have been awarded for works on these models. So I think this is the reason why I think this is a good way to introduce yourself to statistical mechanics, because these are models that everybody knows about, right? So if you talk to the communities, you will basically not, if you work on this, you don't need to explain too much what you're working on, because people know about it already. And also the techniques that have been developed for these models, they can be applied to, they can and they have been applied to other models. So it's a good way to start. So the names here are Werner, 2006, Smirnov, 2010, and Duminil-Copin, 2022. Okay, so now let me say something that is common to these two models. Okay, so these two models are models that are defined on lattices. So let me define what's a lattice. Okay, and basically, a lattice, it's, well, simply a graph which is infinite and periodic. So I will not, for periodic, I will really rely on your intuition and not make a formal definition of what this means. For the sake of this course, it won't make, it won't be a problem, okay? Because if not, I would have to stop and define actions on graphs. Okay, this would be a mess, so I prefer not to do it, and I think this won't be a problem. So let's start, okay, to define what is a graph. So a graph G is a pair which is composed of a set of vertices and a set of edges. So and so the set of vertices is really an arbitrary set of labels, if you want. We will see concrete cases in a moment. The set of edges, it's just a subset of the set of pair of vertices. Okay, I'm just using this notation. It is the set okay, so I'm using this. Okay, this symbol, I don't know. I don't remember the name. Jogo da velha. For cardinality. Okay, so in particular, okay, edges. You have no loops as edges, and I'm not considering graphs which have multiple edges between two vertices. Okay, so now I will give you examples of periodic vertices. So the one we will use more are the following. So I will not use this notation, but I'm just introducing it now because I'm saying that a graph is a pair, which is a set of vertices and a set of edges. So the d-dimensional lattice, it's a graph for which the set of vertices is ZD, and the set of edges is ED, where ED, well, it's just the usual set of edges, so it's the pair of vertices that are at distance 1 in the L1 distance. Okay, so it's a set of xy such that the sum from I equal 1 to t of xi minus yi is equal to 1. Okay? Okay, and just for all the rest of the course, I will just say ZD for the lattice LD. Okay, we just improperly identify the lattice with the graph with a set of vertices. If this is fine with you. Okay, so this is for d equal 2. Okay, and in more dimensions, I cannot really draw. So okay, maybe d equal 3 is a cubic lattice. It becomes a mess. And in dimension 4 and more, it becomes more difficult. In dimension 2, somehow, there are other lattices that I will briefly talk about. So, first one is the hexagonal lattice. Or honeycomb lattice. Okay, so it's just a lattice that you obtain by packing hexagon. So and another one is the triangular lattice, which is okay. Okay, so this is exactly what you want. Okay, this is if you want to draw it with all edges of equal length. Okay, this is what you have to do. Okay, so basically here in both cases, you can define the set of vertices as being some subset of R2, okay? And the edges are the pair of subset, the pair of vertices that are at distance 1. But you don't, I mean, really you can rely on this picture and reason with this picture. I think this will be fine for all the applications. Another way to see the triangular lattice is just to say it's Z2, but you're adding the diagonal in each of the squares here. Okay, you're adding a diagonal edge. So it's not exactly the same picture, but here we are only caring about the graph structure. So in terms of graph, it's exactly the same picture. Okay, so any questions about these definitions? Okay, so now let me kind of introduce what percolation is. So it's a model that was introduced by Hammersley and Welch in the 50s, and I think the original objective was to have application for oil prospection, something like that. But, you don't have to use it that way. The idea is to describe a porous material. So let's imagine that basically you have a solid with lots of holes, and the questions you ask is if you pour water in here, will it flow over there? Okay, so that's kind of a simple question. And the idea on how to modelize this is, well, to say that basically inside your material, you have a small lattice. Okay, on each edge of the lattice, you have a small tube. And this tube can be either open or closed. Okay, and you want to know if this system of open and enclosed tubes, if it let water flow through a large, well, through large distances. Okay, so let's try to be more precise about this. What do we mean by this? Okay, so so we start with a graph VE. And, well, you can imagine your graph, okay, either being ZD or a subset of ZD, okay, a small box. Okay, and for each E in E, we will associate an omega E which will take value either 0 or 1. If omega E is equal to 1, we say that the edge E is open. And if omega E is equal to 0, we say that the edge E is closed. Okay, and what we want to do is to do probability. So what we are going to do is to choose these omega E to be random. And the way we are going to choose them is, well, first we are going to say that the probability that omega E is equal to 1, it's equal to P. And the second thing is that we are going to make all the omega E's independent. Okay, so here let me say what I mean by this. So if E is finite, okay, basically what we are doing is we are taking a probability on the finite set 0, 1 to the E. Okay, and what we are saying is that the probability that omega E equal, okay, let me, if I'm fixing a configuration VE in V in 0, 1 to the E, the probability that I find each edge, okay, the probability of the configuration VE, okay, it will just be the product over E in E of P to the VE 1 minus P to the 1 minus VE. Okay, so an edge is open with probability P, it's closed with probability 1 minus P, and if you want to know probability of a full configuration, you just have to take the product. Okay? If E is infinite, this is where you need a measure theory to define things. But what we just mean is that here we have still omega is equal to 0, 1 to the E. The sigma algebra you have to consider on omega is just the product sigma algebra, for those who know what that means. But then we specify that P is the only probability for which, well, the probability is that, okay, if you take my notes, E1, EK plus 1, EK plus M. Okay, so if you take a collection of distinct edges, then you have the probability that the first k edges are equal to 1 are open, and other m edges are closed is just equal to p to the k 1 minus p to the n. Okay, I mean, here if you take one specific configuration and take this infinite product, you will get 0. So it's not very helpful. What I want to say is that something like this is true if you take any finite collection of edges. And well, measure theory tells you that there is only one measure that satisfies this. Okay, so this is what we do. Okay, you take this lattice. On each edge of the lattice, you put a random variable that takes value 0 or 1. You fix a parameter p, and you say that each edge is closed with, is open with probability p, is closed with probability 1 minus p. And the edges that are independent of one another. Okay, so now what is the question that we are going to make about this marvel? So let's for simplify, let's say that the material I'm considering is a square, or if you want, it's a cube, and we are in 3 dimensions. And in order to know if water flows from here to there, I want to know if I can find the path of open tube going from top to bottom. Okay, can you see the path? So remember, we are doing we have oil extraction in mind, so it's not, you're not just pouring water, you're putting high pressure in it. So it will flow even if it will have to go over there. Okay. So, okay, so, well, of course, the answer to this question is, well, the probability that you have such a path is, it's something which is between 0 and 1. Well, in particular, in fact, well, the probability of a configuration, if you look at it, it's a polynomial in P. Okay? And, well, the probability that you have a path flowing from top to bottom, it's, well, the sum of the probability of this configuration that for which you have a path from top to bottom. So it's also a polynomial in P. Okay, so. So in particular, it's something which is continuous in P, and well, we want to study phase transition. We want to study phenomena that are discontinuous in P. So the way we do this is really, what we are doing is, we are going to take, okay, we fix the square, okay, of size 1, and we are going to take the mesh of the lattice going to 0. Okay, so I will take here the size of my lattice to be 1 over n, okay, and make n tend to infinity. And wonder how this probability behaves when n go to infinity. Okay, or another thing is instead of taking a square 1 by 1, take a square n by n and do not do anything with my lattice. Okay. Okay. So, and okay, so what's the idea is that if you take delta to 0 or n to infinity, and if you look at the crossing probability, okay, well, so if you take delta very large, okay, it will still be something smooth, but okay, one thing is that, okay, maybe it's not completely obvious to write a proof of this, but it's kind of intuitive that this probability here should be something that increases in P. Okay, if P is larger, you have more open edges, so water should flow more easily. So it's something that start from 0, end up at 1. And what we aim to prove is in this course is that there is a critical value of P at which this value changes abruptly from 0 to 1. Okay, so for a fixed size, basically, you see something smooth, but once you take a system of infinite size, which is kind of natural, because if you remember, when you have a porous material, okay, the holes you are looking at, they are really small compared to the size of the material you have. Then you start to see discontinuity in the system. Okay, and so the idea is will be okay first to kind of prove that this picture holds. Then to have some idea of the properties of the system of open canals when you are in this phase and water flows. Okay, and also an important thing will be to okay, so in general, it's kind of difficult to identify what PC is. Actually, for ZD, D larger than 3, it's not expected that it's possible to identify what PC is. Like PC is a transcendental number that probably has no simpler expression than just PC. But for some specific reason, on Z2, PC is equal to 1/2. And this is something that we will, okay. We'll first try to see why this should be the case and to see, then to prove it. Okay, so once we advance a little bit through the lecture about percolation, okay, I will also announce more advanced objectives that we will have. But I think this will be the main thing. Like understand this picture, understand what PC is, and describe some properties of what happened in this phase. Okay, so any questions so far? Okay, so I think a good thing to do as an introduction is to talk about another statistical mechanics model, which is self-avoiding walk. So basically, you see here I have drawn a path on the lattice, which is, well, just a path that never comes back to itself. Okay? And, well, it turned out that, people have studied that, and that it will be an instrument in order to study this percolation phase transition and to obtain bounds about this PC. So, counting self-avoiding path. Okay. So, okay, let us place ourselves on ZD, or more precisely on the lattice LD. And, okay, I will define Sn0 as the set of lattice path of length n starting from 0. So what do I mean by this? What is a lattice path? So a lattice path is just a sequence of vertices, and okay, I want them to start from 0, but this is not part of the definition of a lattice path. And what I want is that basically any point in this sequence is a neighbor of its predecessor. What this relation means, okay, x is a neighbor of y, means that xy belongs to E. Okay, and I will use this notation for any arbitrary graph. Okay, so Sn0, it's a sequence of n plus 1. It's the set of sequences of n plus 1 vertices starting from 0, and okay, that are lattice paths in the sense that okay, the consecutive members, consecutive terms in the sequence, they form edges. Okay, so one thing you can say about lattice passes in periodic lattices is that they are easy to count. So if you want to look at the cardinality of Sn0, well, you just have to look at, well, okay, you have no choice for the first lattice, for the first vertex. And for the other vertices, okay, you just have to choose the value of the increments. And you know that the increment, okay, has to be a vector of length 1 in ZD, and you have only 2D choices. Okay, so it's just 2D to the n, because at each step we have 2D choices for xi minus xi minus 1. Okay. So now let me introduce a set which is not easy to count, which is a set of self-avoiding path. Square I okay, so self-avoiding paths, they are just lattice paths. Okay, yeah, they are self-avoiding paths starting from 0. Okay, self-avoiding paths of length n starting from 0, from the origin. Okay, and they are just lattice paths that are not allowed to go back on their on sites that have already been visited. Okay, so just a path like this one. Okay, and the question is, what is the cardinality of Sn? Okay, and well, the answer turns out to be kind of complicated. So, for instance, when d is equal to 3, I think the best that a computer can do is compute Sn for L is equal to 30. So having an exact expression is really not an option. Here, it's a difficult computational problem to know the cardinality of Sn. So let's try to know what we can say about it. Let me just call this Cn. So what we can say is that Cn grows exponentially fast, okay, but in a rather precise manner. There exists a mu such that Cn, it grows like mu to the n. Okay, in the sense, okay, this means that Cn is equal to mu to the n plus little o of n. Okay, so it's not a sharp asymptotic. Okay, mu to the little o of n, it can be something really large or really small. Okay, but okay, at least we know the asymptotic of log Cn at first order. Okay, so let's try to see how we prove this. Okay, and the key point here will be to prove that the sequence Cn is submultiplicative. So let me tell you what this means. Okay, so here is the lemma that we are going to use. So if you have a sequence which grows at least like C to the n, and which is submultiplicative in the following sense, that a n plus p, it's always smaller than the product of a n times ap, then an grows exponentially with a rate mu, which is larger than c. Okay, in the sense that I've given before. Is the content of the lemma clear? Okay, so this is something which is kind of classic. It sometimes appears under the name of Fekette's lemma. Okay, and usually it's proved for not submultiplicative sequence, but subadditive sequence. But it's exactly the same thing. Okay, so you can say, okay, let's imagine, for this statement, you have a corresponding statement for the sequence log an. Okay, log an, it's subadditive. It grows more than linearly, and 1 over n log en converges. Okay, so as an exercise, okay, you can just write as a corollary a statement about subadditive sequences. Size. Bn larger than Cn and Bn plus p smaller than Bn plus Bp. Okay, maybe I put a D here. Okay, so what we are going to prove here is that in fact, an to the 1 over n converges to its infimum. Okay, so we set mu to be the infimum for n larger than 1 of an to the 1 over n. Okay, and this is larger than C from assumption 1. Okay, so we don't have to. We just have to prove that an to the 1 over n converges to mu because we have for free that it's larger than C. Okay. So now what do we do? Basically, we already have that an to the 1 over n is larger than mu for every n larger than 1. So yeah, I should put the quantificator before. So we just need to prove that lim sup when n goes to infinity of an to the 1 over n is smaller than mu. Okay, and what we will actually do is to show that this is smaller than mu plus epsilon for an arbitrary epsilon positive, okay, which is exactly the same thing. Okay, so let us fix epsilon positive. And we fix n0 such that a n0 to the 1 over n0 is smaller than mu plus epsilon. Okay, so this we can do because mu is defined as the infimum. Okay, so for instance, n0, it's not necessarily large, actually. It could be equal to 1. Okay. And now for n arbitrary, we are going to consider the Euclidean division of n by n0. So n, it's equal to q times n0 plus r, where q is the Euclidean quotient and r is the rest of the division. So r is something that belongs to 0 and 0 minus 1. Okay, and I forgot to say, but I'm going to use these double brackets for intervals of integers. Okay, most of the time I will use it for a and b in z. Okay, but it makes sense also for a and b in r. Okay, so okay, q there are. It's implicitly it's q of n, okay, and r of n, and they are uniquely defined just by this property. Okay, so now if I look at an, I know that it's just n minus n0. Okay, just assume that n is larger than n0 for a moment. So sorry, it's equal to this. And using subadditivity, it's smaller than an minus n0 times a n0. Okay, and now I can just iterate this, so I can say that this first term here, it's smaller than a times n minus 2, and 0 times a and 0. You're just doing the same decomposition. And if I do this, well, either q times or q minus 1 times, I get that this is smaller than AR times a and 0 to the q, where a0 is equal to 1 by definition. Okay, my sequence is starting from 1. So I have the freedom of defining a0 as I choose, and you can see that this is the right thing for this to be true. Okay, so now AR, I can always say that it is smaller than the supremum of AI in this range. So I don't want to have something that depends on n here. So, but now. Okay, so now if I take everything to the power 1 over n, I get this. Okay. So now what can I say? And 0 is, okay, what we want is to make n tend to infinity. You know that n0 is fixed. So this sup to the 1 over n, this tends to 1 when n goes to infinity. Okay. And the other thing you know is that q over n, well, this is smaller than 1 over n0. Okay, just from this relation. Okay, and a and 0 is larger than 1. Okay, so this means that this thing here is smaller than a and 0 to the 1 over n0. Okay, so overall what we get is that the lim sup when n goes to infinity of a n to the 1 over n, it is smaller than 1 times a and 0 to the 1 over n0, which is equal to nu plus epsilon, which is smaller than nu plus epsilon. Any question about the proof? Okay, so now let's use it to show that the number of self-avoiding paths has a growth rate. illustration of the proposition. Okay, so, well, the first thing we need to show is that Cn, okay, which is the cardinality of Sn, is larger than d to the n. Okay, this is the assumption 1 over here. Okay, and so let me define, okay, this is not, E is for edges, so let's, okay, V is for vector maybe. So let me define Vi as the vector 0, 0, 1, 0. This is ith position. Okay, so we know that if xi minus xi minus 1 j belongs to Vj, j equal 1 to t for every I in 1. And then xi I equal 1 to n is self-avoiding. Okay, so a way to get a self-avoiding path is to go only through the, if you want, the positive direction of the axis. If you do this, you're kind of sure that you never visit a site that you've already visited. Okay, and the number of ways to choose a path that satisfies this is clearly d to the n, okay, because you have d choices to choose a vector of the base of your lattice. And really, you're allowed to choose any vector at each step. So. The number. Okay, so in dimension 2, okay, it's just paths that are just going to the left and to up and left. Okay, so now we have to show the second thing, which is that our sequence is submultiplicative. Okay, so for this, what I will do is to construct a function from this set to this set, which is an injection. So, I mean, of course, the cardinality of this is Cn plus P, and the cardinality of this Cartesian product is Cn times Cp. Okay, so if we show that there is an injection, then the cardinality of this is smaller than the cardinality of this. Okay, so what's injection? Well, okay, maybe I can make a picture here. 0. I think I have n is equal to 8, and p is equal to 14. Okay, and okay, the idea is the following. If I have a self-avoiding path of length n plus p, I can obtain a self-avoiding path of length n and a self-avoiding path of length p in the following manner. So for the self-avoiding path of length n, I just take the first n steps. Okay, and for the self-avoiding path of length p, well, I take the other p steps, and I have to shift this back to 0. Okay, and to see that it's injective, well, you just have to show that if you're given the blue path starting from 0 and the red path, you can reconstruct the full path, okay, just by gluing them together. And it's not surjective, okay, because if I'm giving you two self-avoiding paths, when you glue them together, it's possible that they will intersect. Okay, so this will tell you that this inequality actually here, it will be strict, I think, as soon as n plus p is larger than 4. Okay, so what is this bijection? Xi I equal 1 to n x n plus j minus xn j equal 1 to g 0. Okay, and here there is no problem. When you write it like this, you see that this thing, I mean, it arrives in this space, okay? Well, the fact that it's a lattice path, it's easy to check. The fact that it's self-avoiding also. Here I've deleted xn, so I'm sure that I'm starting from 0. And the fact that it's injective, well, it's not difficult to construct the reciprocal. Okay, so this gives me that Cn plus p is smaller than Cn times Cp, and this concludes the proof. Any questions? Okay, so I've written these things for ZD, but actually you can make this thing work for any periodic lattice. So, for instance, yeah, here, of course, I mean, you can see that the spirit of the proof completely works. It's not really clear what you should write here if you're considering the hexagonal lattice, for instance. But the picture works. So the proof works as well. Okay, and I think now I can leave you with a bunch of exercises. So now the question, the natural question to ask is, what's the value of mu? And on ZD, basically, the answer is mu is equal to mu of ZD, and there is no better expression than that. Okay, so people don't believe that there is a special expression for mu, but okay, there are things that you can that you can say about it. So let me leave that as exercises. So show that mu of ZD is strictly larger than D. Okay? We've shown that it's larger than D. Well, try to just do a tiny bit better and show that it's strictly larger than D. Because it sounds quite reasonable. The second thing you can try to do is, well, consider the ladder lattice, okay, which is just, well, the two first rows of ZD, okay, and fix a point to be equal to the origin, and try to compute the connective constant of this. Okay, so try to prove that mu is equal to the golden ratio for this lattice. Three, maybe show that mu of ZD is smaller or equal to 2D minus 1. And then try to prove the strict inequality. So maybe for the strict inequality, maybe you can restrict to D equal to 2. Okay, so smaller than 2D is completely trivial because we have seen that 2D minus 1 is a bit more difficult, and strictly smaller, it's kind of comparable to this. Okay, and now to conclude, let me tell you a bit more about. Okay, this is kind of a a very rough first order result. So, what more can you say about the number of self-avoiding paths? So. Maybe first thing I can say is why people wanted to count these things. And the idea is these self-avoiding paths, they have been introduced as a model for polymers. Okay, so polymers are just molecules that are periodic and that are made of individual monomers. So, and you want to understand how what will be the way what will be the typical spatial configuration of a polymer. Okay, and maybe there are lots of things to be taken into account, like interactions between different parts of the molecule, but the first thing you can say is that maybe one location of the space cannot be occupied by two monomers. Okay, so the first thing that people have been so I've said so far self-avoiding path instead of self-avoiding walk because for me, I think the most natural thing is to say that the self-avoiding walk is a measure. Well, it's a process. Okay. which is defined as follows. So it's a probability, it's a random variable which takes value in the set Sn, and okay, let's see. And the probability of a given configuration is just uniform in Sn. Okay, and what people wanted to understand, so this was introduced by Flory, I think it's 48. And what people wanted to understand is what is the typical behavior of this process. So if you don't have this self-avoiding constraint, it's kind of, you know what's the typical behavior of a configuration is. Okay, basically the central limit theorem tells you, okay, the Donski's theorem tells you that your typical trajectory will look like a d-dimensional Brownian motion if you rescale it by square root of n. So in particular, okay, it will tell you that xn minus x0, this will be roughly over the square root of n. Okay, so what people have wondered is what is, under this measure, the typical distance between the two endpoints. Okay? And what is believed is that xn is typically of order n to the 2/3. Okay, so maybe there is a little of 1 here, but anyway, this is really difficult to prove. So far, there has been almost no progress on this conjecture in dimension 2. Okay, so this is for d equal to 1. Okay, for d equal to 3, okay, it's believed that xn is something like n to the chi for some value of chi. I think Flory conjectured that the value should be 3/5, but it has been kind of disproved by numerical simulation. So now it's not believed that chi should have a specific value, and this is probably even more challenging than this. Okay, when d is larger than 5, okay, it is known that actually your walk typically behaves like a Brownian motion. Okay, so dimension 5 is in a sense easier because, okay, somehow if you take two random walks in dimension 5 without the self-avoiding constraint, they typically don't intersect each other very much. Okay, so this self-avoiding constraint is not, if you take two infinite random walk in dimension 5, the number of intersection is typically finite. In particular, they have even 0 intersection with positive probability. So for this reason, the self-intersecting constraint is really a local constraint in that case. And it does not change very much things on large scale. Okay, so basically what this does here, I mean, it's not an easy result at all. But the phenomenon, it's kind of easy to understand. What this self-avoiding on small scale, it will just change the variance in the central limit theorem. Okay, so you will be slightly more diffusive. In smaller dimension, it's much more challenging, and I think the best result up to date is that xn is typically much smaller than n. Okay, so this seems completely trivial. Okay, to say that the walk doesn't go ballistically, well, I don't know, it would be very strange that the walk would choose one direction and go with a positive speed in that direction because of this self-avoiding constraint. But this is the best that has been proved. And they have, okay, so like from their proofs, you can extract somehow an explicit bound here on how fast this ratio should go to 0 typically. But they didn't bother to do it, and I mean, probably what you get is something like the inverse tower function, or something that goes very, very, very slowly to 0. Okay, so just to give you some conjectures over there. Okay, so this problem, it's really, really related to the counting of the walks. So now let me tell you something about the counting of the walks. So what is believed is that Cn typically, okay, so what you already know here from you know that mu is the infimum of Cn to the 1 over n. So you know that Cn is larger than mu to the n. Okay, what is believed is that Cn is equal to n to the power, let's call it nu, times plus little o of 1 times mu to the n. So the value of mu is not believed to be something specific, but it is believed that what you have in front is just a power of n with some specific exponent, and when d is equal to 2, this exponent should be 11 over 32. Okay, and okay, people are kind of very far to prove this. But there have been some steps in that direction. So let me tell you basically what has been done. So okay, and this exponent it's known to be 0 in dimension 5 and more. Okay, so okay, so what is known actually in dimension 2 is the following. So for that, so it's actually believed that here this exponent here, you should not believe it should not depend on the lattice you're considering. So it should be the same for any two-dimensional lattice. So it should be the same for triangular, honeycomb, and Z2. Okay, and for some magic reason, the value of mu is known for the honeycomb lattice. Okay, so this was somehow conjectured by Ninius, a physicist in the 80s, using some physics arguments that are difficult, well, that have not been made rigorous, and it's kind of difficult to understand. But another approach using what are called parafermionic observable has been adopted by Smirnov and Duminil-Copin. Maybe Duminil-Copin and Smirnov. In 2010, and okay, they proved this. And basically, if you know the value of mu, well, you can do some more. And okay, the idea is that maybe you can have some more precise counting and have some better boundaries. Okay, because from now on, in general, the best bound you have is that Cn is smaller than mu n times exponential of square root of n in dimension 2, which is kind of far away from this. Okay, and I don't know, maybe we'll try to explore this proof. It's a very nice paper. It's only 8 pages long. It's also, the proof is also presented in the notes of GRIMET. And okay, it's kind of a funny story because the note of GRIMET, they are about a course that was lectured in 2008. So the thing was not proved yet. And I know that Duminil-Copin was in the audience because I was also in the audience at that time. So during the course, this was presented as a conjecture, but now the lecture notes have been updated and there is a proof of the result. Okay, and I think this is what I wanted to say so far today. So do you have any questions? Okay, so I think we will see back on Friday. Okay, I will update my web page to include all the list of references. Okay, so please let me know if you have any questions. And yeah, you can send me questions by email. You can also prepare your questions and, at the beginning of every lecture. I will try to dedicate some time to questions if there are some. Okay, so see you on Friday.